Okay.
Perfect. So now it should be in progress. Perfect. Yeah, well, thanks, Andrea, for the very kind introduction. And also obviously thanks to the for having me and giving me the opportunity to talk a little bit about work that normally I don't get to talk all that much about. That is very dear to my heart, but it's also very abstract and kind of foundational, I would say. So it's really, I'm really happy that I get the opportunity to talk a little bit about this resource theory of causal connection that I've worked out together with Jessica Barbaresco and Julie Curiabella, using a lot of techniques that actually only published later that I only published later together with Marco Tullio Quintino. So today I want to talk a little bit about like what I would call the resource theory of causal connection. I could have just as much have called it fun with higher order quantum operations, because that's what we're going to do a lot. So you're going to see a lot of these drawings here, and obviously I'll explain what they pertain to. But you'll see a lot of these drawings, and I try to keep the math basically most of the time under the hood and will mostly operate in drawings. And so the two questions that hopefully by the end of the talk I will have answered are the first question, how valuable is the ability to send signals between quantum parties? And the second one is a little bit more technical, and I hope I get to it. Last time I gave this talk, I didn't, but this time I have an hour, so I might throw a little bit of the technical background at you. But just the question is the more general question that goes a little bit beyond this question of signaling, which is how can we easily derive the properties of higher order quantum operations? And obviously, I'll kind of tell you a little bit more about what these two questions actually mean. So let me start motivating this question of causal connection, and let me start at something that we all know and that is very dear to our heart, which is spatial quantum correlation, so i.e. entanglement. So as we all know, and I really don't have to motivate that all that much, entanglement, or in more generally steering and non-locality, these are quite interesting and quite like technologically relevant resources in quantum technologies. So when I talk about entanglement, I always think of like two parties, Alice and Bob. They are spatially separated and they share some quantum state, which throughout I will always depict as such a triangle with lines coming out, just meaning that one part is Bob's, one part is Alice's, and they share entanglement. Now, however, in order to do something useful with this entanglement, normally it's not enough to just share entanglement, but I also have to process it somehow. And for that, I need to send signals between the parties. So for example, what I could do is I could take this entangled state between Alice and Bob. Alice could make, together with some state that she also prepares, she could make a measurement on it, and then send her measurement outcome, signals her measurement outcome to Bob, and he could do some control operation here. And well, most of you will have directly gathered that this protocol is like defined as quantum teleportation protocol, which if you run it correctly, in the end, you will have teleported the state on Alice's side down to Bob's side. But what it requires is not just the entanglement between Alice and Bob, it also requires signaling between the two parties. In this case, it's only classical signaling. That is, Alice only has to signal classical information to Bob, but nonetheless, this protocol contains two resources. One is spatial resources, i.e. entanglement, and the other one is signaling between the two parties. Now, throughout, I don't want to really talk about what's happening on a microscopic level. So what I'm going to do throughout is I'm basically going to put everything that is protocol, put everything that pertains to things that the two parties cannot really control. I'll put it under a big box, like so, which is basically a box where Alice could put in her operation. In this case, it would be measuring, if you think back, measuring and feeding information forward. And Bob could put his operation in, which in this case is just the control operation that he does. And between them, there would be some kind of signaling that happens. And now this higher order map, well, why is it higher order? Because it's basically an operation in which Alice and Bob could plug in their respective control operation or their respective maps that they want to perform. And this object, as we shall see, contains all spatial temporal correlations that Alice and Bob can share. Spatial ones would, for example, in this case, be the entanglement between Alice and Bob in the beginning, and the temporal ones would be all the signaling correlations between them. In this case, the ability of Alice to signal forward to Bob. And now what I want to now in the next hour, what I want to talk about is in these kinds of scenarios where Alice and Bob can communicate with each other, not just classically but quantumly, how can the signaling resources in such a scenario be quantified?
So,
No,
Simon, I have a quick
yes,
question. Sorry to
yes, of
interrupt.
course, of course,
So,
no.
how do you distinguish between classical versus quantum signaling here?
That's a very good question. Can I come back to this later?
Sure,
Because I think
sure,
it
sure.
makes more sense later. This is a very good question. I will,
Okay,
so just as a disclaimer, throughout this talk, I will not. I will just talk about signaling, and it can be classical or quantum. Let me get back to that in like 5 slides.
sure,
Then
sure, sure,
it's much easier to talk about it. Perfect, but good question.
sure,
Yeah,
sure.
please, obviously, please feel free, all of you, to ask questions.
All right. Cool.
Yes. So, but maybe piggybacking on to Shrikant's question there, like here it's a little bit boring, maybe the signaling that we see because it's just classical. We could obviously think of a more complex situation. Say you could have users in a quantum communication network or or distributed quantum computation, where you have some kind of unitaries that might be your circuit, that might be your computation. I just drew it here in a very abstract sense. And you have some users, A, B, C, D, and E, that are distributed in space and in time, and they wanna together either communicate or compute something. So in this case, again, if I make this a little bit abstract, you'd have this box where Alice, Bob, Charlie, Dave, and Eve, they can all plug their operations in, and there's kind of signaling between all of them. And in general, if I really want a quantum advantage, it would not just be classical signaling, but I could also signal quantum states. I could also signal quantum information. And so again, the resource in such a scenario would not just be entanglement in space, it would also be kind of what I want to call entanglement in time. And Shrikant, I get to your question in a second then. Yeah. Okay. So again, the question is, in these scenarios, how can we actually quantify this resource of signaling? Because we're really used to quantifying the resource of entanglement in space. So here the question is, how can we actually do this for signaling resources? Okay, so little disclaimer. Here I've drawn like 5 parties. From now on, I'll mostly do it for 2 parties, mostly for drawing purposes because it's easier to draw. It's not really necessary. I could do it for more parties, but then everything would get a little bit cluttered. So it's much nicer to actually do it for 2 parties. So from now on, most of the talk will be about 2 parties. So in this case, just to make this, like to make this a little bit more specific, we could think of different types of communication scenarios. So for example, we could have a scenario where Alice has a laboratory and she can open a hatch and maybe a quantum state flies in. She can do something to it, like represented here by the cogs, like she can do some kind of operation to it, send forward whatever comes out of that operation, sends it to Bob, and because we only have 2 parties, whatever Bob sends out is basically thrown away. So that would be a communication scenario where Alice can send X to Bob, where X could either be like in the teleportation scenario, it could be a classical label. It could also be a quantum state that Alice sends forward. And I want to depict or I want to denote such scenarios as A preg B. So A comes before B. And the overall scenario, I'm going to denote by a W, A before B. Now, naturally, you could also have it the other way around. You could have a scenario where, say, Bob can open a hatch, gets a quantum state, does something to it, sends it forward to Alice, and then whatever Alice sends forward is thrown away. So that would be a situation where Alice can, sorry, I screwed up my slide there. Obviously, this would have to say Bob can send Y to Alice. Now, naturally, we can also think about like something where sometimes Bob can signal to Alice, sometimes Alice can signal to Bob. So basically, I could think of a situation where with probability P, we have a scenario where Bob can send information to Alice, and with probability 1 minus P, Alice can send something to Bob. So for example, I could just flip a coin, which would kind of give me a probabilistic mixture of 2 different orders, of either 2 different signal directions, or if you want to think about it in terms of causal orders, you could also say it gives me a probabilistic mixture of causal orders. And throughout, I'm going to use like the ability to send signals. I'm going to use this interchangeably with the idea of causal connection. So 2 parties are causally connected if one can send a signal to the other. Now, finally, Finally, in quantum mechanics, we can also think about situations that are outside of this nice convex mixture of causal orders. We can cook up the situation, and I will kind of explain later on how to mathematically get them. But we can kind of have a little bit more in quantum mechanics and without kind of breaking logical consistency. And we've known this like for the last 13 years roughly. Little disclaimer for those of you who are not happy with such processes that seemingly are not a convex combination of ordered things. It's not crucial for this talk. It's just a nice superset of all processes that we can have. And finally, if we talk about signaling, obviously we want kind of the baseline. Basically, we want the object that is the resource, like the process that is the resourceless one, which would be the one where, well, Alice can receive something and send it forward, and Bob can receive something and send it forward, but they can't communicate with each other. So I kind of will depict this also by this B parallel with A, meaning neither party can signal the other. Naturally, there is a special case of Alice being able to signal to Bob, or Bob being able to signal to Alice, is basically the intersection of these two sets. But so that will be the baseline when we talk about signaling. These are basically the processes that absolutely are resourceless. And we will use these processes to kind of gauge the resourcefulness of other processes against. So what we get in terms of the processes we're going to look at, or the signaling scenarios that we're going to look at, is basically this. So we have a set of processes where Alice can signal to Bob. This is this ellipsoid here, or this comic here. We have the set of processes where Bob can signal to Alice. Then the intersection of the two of them is the set where neither of them can signal to the other. Then we get the convex hull of them, which is the probabilistic mixture of signaling processes, which denoted by W-sep, because it looks a little bit like, like inspired by basically this idea of separable states. Here we basically have like causally separable processes. And then finally, there's this superset of processes, as I said, that we can think of in quantum mechanics, but they lie outside of what we can basically describe by a convex mixture of definitive causal orders. And again, now for these sets of processes, we now want to ask the question, if I have a process somewhere, how valuable is the signaling content of it? Now, in order to answer that question, we can attack this question in a sense in two ways. So first of all, we can kind of work out a quantifier of causal connection, or of signaling. We can work out some kind of functional that when I plug a process into it, it tells me this process has, I don't know, X amount of signaling in it. On the other hand, we can also ask the question, or like kind of related to that, we can also ask the question, well, what kinds of processes can be converted into each other without any kind of signaling or without any kind of communication? Meaning that if I have some process and it can be converted into another one without using any kind of signaling, well, then the first process must have been more valuable than the other. So what this tells us is, or this two-pronged approach basically leads to two ideas about how to go about quantifying or understanding signaling in quantum processes. One is via resource monotones, that is functions that basically just quantify how much signaling is in a process. And the other one is through free transformations, that is transformations of processes that don't themselves introduce any kind of communication, or that don't introduce themselves any kind of signaling. And then we can ask the question, can one process be transformed into the other by means of such free transformations? And if so, then the first process is more valuable than the second. So maybe those of you who have heard of resource theories, they will be like, okay, yes, this is kind of now what we play now is basically the normal game of resource theories. We have some set of free objects, which would be the non-signaling processes here, which would be those ones. So these are the free objects. These are the things that have zero signaling content. And then we will kind of have to work out what are free transformations. That will be transformations of processes that do not introduce any kind of signaling themselves. And the mathematical question that hopefully I'll get to in the end is a question of, well, can we actually work out the properties of such transformations? those of you who have worked with resource theories will will know that this is kind of the normal machinery of resource theories. Is just a little bit like played on a higher level in the sense that normally free objects are states, and the transformations of these states are mappings, are quantum channels. Here we basically go play the whole game on a higher level, where we say our free objects are actually processes, and the transformations thereof are transformations of processes. But conceptually, the idea is exactly the same as for run-of-the-mill normal resource theories. Okay, so in order to talk about this properly and to get to Shrikant's questions, actually, let's look under the hood. So now I've kind of introduced all of this in a very abstract way. Let's look under the hood. What do these respective processes or sets of processes actually look like? So, for example, take a process where, again, Alice can go before Bob. But again, as I said, you could have like that Alice can do an operation and send whatever she did forward to Bob. Now, if you look at the underlying quantum process, the most general scenario that pertains to is basically a scenario where Alice can do some operation on a state or on a part of a state, and then together, whatever she sends forward and the rest of the state go through a quantum channel, and then Bob can do some operation on it afterwards. So that's the most general scenario where Alice can signal to Bob. That's all there is. Now, to make this a little bit less abstract, what Alice and Bob generally do are quantum operations. That is, they do like some CP maps, and CP map is just basically they can do any kind of measurement or any kind of dynamics that they can implement, basically. And again, we could just draw this box around it that kind of contains, if you look back, that kind of contains everything that Alice and Bob don't control. We draw this box around it and call it the underlying process. And that object actually contains all pertinent information. It contains, if you look back, it contains spatial correlations that are basically the correlations between the system here and this auxiliary system, and it contains all the signaling content. So this object, once I have it, describes everything there is to know about this underlying process. So, for example, if Alice performs some measurement and Bob performs some measurement, then the probability for the respective outcomes that they get, I could just get from plugging it into this kind of abstract object, which we denote by the underlying process that is there. Now, that's a little bit of an abstract thing. It's some mapping that takes maps to probabilities. That's a little bit abstract. It gets much nicer if we map the whole thing to quantum states. And we can do this via the Joya-Minkowski isomorphism. So that's basically just a mapping that says, okay, this abstract object, this abstract yellow object here, that takes quantum operations and plugs them to numbers. I can just as much write this in terms of some matrix acting on matrices that correspond to these measurements here. So then WA before B has kind of the structure of a quantum state that internally encodes all the correlations and the signaling structure of the process. And now, Shrikant, we can actually nicely talk about the question you had, because given that it's a quantum state, I can talk about that thing's correlation structure. And if there is entanglement between basically the system that corresponds to Bob's part and the system that corresponds to Alice's part in the state, then there is quantum signaling between those two. If, however, the correlations in there are only classical, then there must have been only classical signaling. So maybe that was a little bit quick, but what I want to say is I'm not going to talk about this in any more detail, but basically the correlation structure in this object, in this quantum state that pertains or that corresponds to this process, tells us something about what kind of signaling does the underlying process allow for, depending on whether or not it is entangled between the respective subsystems or not. So let me make this a little bit clearer. Let's do it. I think this is the only slide where I really have math on. So just to be a little bit clearer, these objects, Alice and Bob, like the operators that correspond to their measurements, they live on some Hilbert space input and output. So basically each of these maps has an input space, it has an output space, and the corresponding matrix that describes it lives on the tensor product of the input and output space. And the same for Bob. And correspondingly, the matrix here that describes this process lives on this tensor product of these four Hilbert spaces. So now you could kind of, Shrikant, come back to your question. Now you could say, well, if there's entanglement in this state between AIAO and BIBO, then there must have been actual quantum signaling between the two. If there's not, then there's only classical signaling between the two. I hope that answers your question sufficiently.
Also, so I have a
Yeah.
quick thing to ask again here.
Yeah.
So this WA
Yeah.
to B, right?
Yeah.
Or B to A.
Yeah.
So
A to B. Yeah.
this object should violate some kind of causality inequality to say that it has quantum signaling, right?
No. So that's I think that's true. That is true. I think if you were to work out like the pseudo density matrix of this, but this is not a pseudo density matrix. This is
even in the process tensor process matrix language.
Yes.
So should it violate some kind of causality inequality?
No. So this object at the moment is fully causally ordered. We really got it from an underlying circuit, so it shouldn't violate any kind of causal inequalities. I'll get to a process matrix that does.
Okay.
Yeah.
Sure.
Okay. So I said this thing is a quantum. This corresponds to kind of a quantum state. So it is positive, and it's not quite a quantum state because it's not trace normalized. It has like the trace of the dimension of this output space times the dimension of this output space. But up to that, it's a quantum state. Now, causality, and thank you, Shrikant, for kind of setting up all my future slides. This is really good. What does causality now mean in this case? I mean, obviously, this is causally ordered. Alice comes before Bob. Well, causality means that whatever Bob does here, it should not influence what Alice sees. So basically, if Bob performs some kind of deterministic operation, say a unitary or in general a quantum channel, then what Alice sees should be completely independent of what Bob did. Yeah, so causal ordering just means whatever Bob plugs in here, what Alice sees locally is completely unaffected by that. But not the other way around. Depending on what Alice does here, certainly what Bob sees changes, because otherwise there'd be no signaling between them. And that kind of this constraint or this demand of causal order kind of translates to two more constraints on this quantum comb or process matrix object here, which is basically that that this process matrix kind of factorizes into an identity matrix on this last leg, tensor something, and basically you get two more constraints that are imposed by causality on this object. Now, bringing this all together, we have now talked about Alice before Bob. Obviously, we could do the same for Bob to Alice, and we could then also do the same for no signaling. So again, the scenarios that describe an Alice to Bob signaling are described by these kinds of, I forgot to say what they're called, like they're called process matrices or quantum combs, depending on who you ask. So they're described by these process matrices that satisfy these two constraints. And you can kind of combine them nicely, and we'll get back to that in the very end. You can combine all of these properties kind of nicely by means of a projector. So basically, we can say the process matrices that describe a situation Alice before Bob are given by those that satisfy that they're invariant under a certain projector. And this projector just combines these two causality constraints here. Bob to Alice is the same, just with the systems A and B interchanged. And finally, the no signaling ones are very simple because these are exactly the process matrices that correspond to a state on Alice's and Bob's input, so some fixed state on Alice and Bob's input, tensor just a boring identity matrix on A naught and B naught. So, and again, these sets mathematically can very nicely be characterized by a projector, by a self-dual unital projector. Self-dual and unital not so important. Basically, all I want to say is these things are described by matrices that live in some vector space, and that vector space can be characterized by a projector. Now that tells us that at this moment, we have kind of a nice characterization of these three sets, of the non-signaling one, and the A to B signaling one, and the B to A signaling one. What remains is this last set. This last set is not given by any kind of like by a specific signaling constraint, but it's just given by the demand that if Alice and Bob do something, that should happen with probability 1. So for example, if they implement a unitary, or if they implement more generally a quantum channel, that should happen with probability 1. So that means that the trace of our process matrix with these two maps, whenever they correspond to CP-TP maps, think of unitaries, for example, then the outcome should be 1. And this encodes local causality, meaning that Alice and Bob should not be able to travel back in time and kill their grandfather or things like that. And again, if you work this out, you can work out that the corresponding process matrix would be given by a nice projector that has been worked out in 2015 by Matteo Geraggio and collaborators. So that means now we get this whole picture of all the processes we can consider. So we get Alice before Bob, Bob before Alice. Alice and Bob cannot signal to each other, and finally the full set is characterized by this general projector. And in general, they should be positive, and the trace is given. Okay. All of this to say, we can have a very nice description of the processes we talk about. Namely, the set of processes we talk about is exactly this whole thing here, this whole set, which is given by all process matrices that lie here that satisfy this overall normalization of probabilities to 1. So in the set of all processes, there's the set of free processes, which is the one that do not allow for signaling between the parties. And as I said earlier, what we want then is the set of transformations. That means the set of maps that take these processes and generally they should map processes to processes, but they should also satisfy that if they act on something that's free, well, they should still spit out something that's free. Meaning that they should not, like the transformation of processes that we're now going to talk about, they should not inject any kind of signaling into our processes. And then again, coming back to this question of, well, how do we now quantify signaling? Well, on the one hand, we could say, well, we can quantify the signaling content in one of these processes by the question of how far it is away from the set of free processes, from the set of non-signaling processes. Mm-hmm. And the second part is to say, well, we can even be a little bit more fine-grained and kind of discover a hierarchy of processes, meaning that like one process is more valuable than another one if I can transform one to the other by means of a free transformation. Meaning that if my transformation of processes is a free one, then when can I basically transform one of these processes to the other by means of such a free transformation? If I can do this, then certainly W1 here is more valuable than W2. And just maybe to give you, so just to be clear, the free processes we talk about have this structure. They're very boring. They are processes that do not allow for signaling between the parties. That means it's basically just processes where Alice and Bob share a state. And then whatever they feed forward, so they share the state row, whatever they feed forward, it just gets thrown away. And there's no communication from Alice to Bob, but there's also no communication from Bob to Alice. Yes. And transformations of processes look like this. So we start out in some kind of process, let's call it W, and a transformation of that would just basically take this process and map it to another one. And in general, we want this thing to be linear. We also wanted, in order to preserve positivity on all levels, we also want it to be completely positive. But those are more like mathematical issues. But like what we're going to look at now is like transformations from here to here in a completely abstract sense at the moment. So I'm not even thinking about how are they implemented, but really just on very abstract grounds, how can we transform one process to another? An example of that would, for example, be, so this is what such a transformation would look like. We take a W and we basically play Lego. Well, we plug in this kind of blue object, which is, I would call this an adapter throughout, because it basically just takes a process, maps it to another one. So you can see this here, this yellow object has one slot originally. Has two slots originally, the top slot and the bottom slot. And after I plug in this adapter object, it still has two slots. And an example of that, yes.
Sorry to interrupt.
Yeah, of course.
Is the requirement of complete positivity obvious?
It's
Because in
not,
it's your
yeah,
process acts on part of a state, but here
yeah,
you want a transformation that acts on part of a process.
exactly. So so it's not obvious in a sense. I could do without, but it's still the question of completeness, of complete positivity, in the sense of I could only act on parts of a process. And if I only and parts of my processes, like a particular process, is one that basically just prepares maximally entangled states. So it's a little bit the same as demanding complete positivity for process matrix itself. There's no a priori requirement for, if you just want probabilities to be positive, it's not necessary that your process matrix is positive itself. But if you want that, it maps whatever it acts on, even if it only acts on part of it, to something positive, then you will really need this complete positive thing. But it's an additional assumption that I make. It doesn't follow from, say, preservation of positivity of probabilities. So it's not an obvious one. It's an extra assumption that I just throw in as an ingredient.
Okay, thank you.
Yeah. Yes. So like maybe coming back to this question, obviously this blue object could also only act on a part of this W. So this, there could be two lines that go in here and two lines that come out of here. This blue object could just only act on a couple of them. But what I would want is that any positive process matrix gets still mapped on a positive object. And if I demand that, then I basically get in the Choi picture, I get positive objects epsilon here. And that corresponds to complete positivity. So it's a little bit of a convoluted concept of complete positivity, but it goes through in a very similar way as for quantum states or for process matrices. To be a little bit concrete, like this is a very abstract object a priori. One that you could imagine would be a transformation that simply comes from sharing a big state, and then Alice and Bob can process this thing locally and make this kind of adapter. So this kind of adapter can come from something very benign, where they basically just share a state and do something locally. We will kind of get back to this kind of adapter because obviously it doesn't allow for any signaling between the two parties. If you look at it, there's no lines that connect the two parties. So we will get to that adapter in a bit. So fundamental requirements that we have of free transformations or free adapters. Well, on the one hand, we want them to be admissible. Well, that just means that, well, they should map processes to processes. And that's a fundamental requirement of any kind of adapter. They should, in a first step, they should be free preserving. That means they should map free things to free things, because otherwise they introduce some kind of a resource. A third one that I could demand that is stronger would be that they should be non-signaling themselves, meaning that if I had access to this adapter, if Alice and Bob individually had access to this adapter, they should not be able to use it to send signals to one another. And finally, a fourth demand that I could have would be that this adapter you should be able to implement it without any signaling resources. So as I said, the first one is just a general requirement for any transformation, free or not. And 2, 3, and 4 are inequivalent, and they kind of increase the level of control over the adapter. In like 2 assumes less control over the adapter than 3, assumes less control over the adapter than 4. And now we basically go through all of these sets and show that they're all nicely contained in each other. So first one is just, something should be admissible. So basically it should just map any process that you plug in it. It should map it back onto a valid process. You can phrase this mathematically as saying, if I have a process that I start with and I transform it, it should still be invariant under this projector that defines the set of valid processes. Now, like this set has been worked out in a couple of different publications, and it basically, if I go through the math, it gives me a convex set of admissible transformations, which I've depicted here as this egg, and the set admissible. Okay, so it gets more interesting now if you demand a second thing, namely that our adapters should be free preserving. So they should be map anything that's free onto a free thing. So if I draw this, it should be such a projector, such an adapter should be such that if I plug in a free object depicted here by an input state and these traces here, should be such that it maps any such object back onto a free one. In mathematical terms, you could again phrase it as, if I start with a free object and I act with my adapter on it, it should still be invariant under the projector onto the set of free operations. Now, again, and I hope I'll get to that in the end, you can work out what the set looks like. Yeah, you can fully characterize all the properties of this set, and it will again lead to a set of, like, it will again lead to a convex set of free preserving adapters. Now, what's almost more interesting than working this out is the question, well, does preservation of free actually guarantee that I'm also admissible? So how are these two sets, is one contained in the other, basically? And the answer is no. So there are adapters that preserve the set free, but they are not admissible. And an example of this is this very simple adapter here. So all it does is it basically swaps the input of Alice with the input of Bob, and it swaps the input of Bob with the input of Alice. Now, certainly, if you think about it, if you plug in a quantum state here, then all it does is it swaps the legs of that quantum state. That means it will certainly map free onto free. However, if you think of a very boring process between Alice and Bob, where in the beginning, a quantum state is prepared, it is sent into Alice's lab, and then there's an identity channel between the two, and then Bob can do the operation. Now, if you apply this adapter, all that happens is we swap the input of A and the input of B. So basically, we say we swap the input of B and go back here, and we swap the input of A and made it the input of B. What that means is that now in this process, Alice would send something forward, and then it would be swapped back into her input. Well, that certainly can't be true. Like, now we're actually closing causal loops, and that's certainly not a valid process anymore. Meaning that there are adapters that map free to free, but they don't map all processes to all processes. So what we get is this kind of situation. We have the set of admissible adapters, we have the set of free preserving adapters, but there are free preserving adapters that are not admissible, and there are certainly admissible adapters that are not free preserving. So that leads us to our first actual valid or interesting set of adapters, which would be the admissible and free preserving transformations, which is exactly the intersection here. And that's the largest set of potential free transformations that I at least can think of. And it's very analogous to, like in the Rhesus theory of entanglement, if you're familiar with that, there's a set of separable operations, which is basically the largest set that keeps as far as I know, that keeps the set of separable state invariant. And here it's the same. Like here, this would be the largest set that is contained of valid operations that also lead the set of free processes invariant. But these are quite powerful because for two reasons. One is there are adapters that are, this shouldn't be LFP, this should be AFP, that are admissible and free preserving, but can change the causal order. So think of this adapter. Basically, this adapter is like the one before, just it does two swaps. It basically changes AI and BI, it changes BI for AI, and it changes the output of A for the output of B, and it changes the output of O for the output of B for the output of A. What that means is, if I have a process that I plug in that is Alice before Bob, because it just swaps the system, afterwards I have a process that is Bob before Alice. So in a sense, from a signaling perspective, that's a very weird thing that an adapter like that can kind of swap the orders of my parties. It can basically map a process that is Alice before Bob to a process that is Bob before Alice. That seems a little bit too strong for a free adapter. And one can also show, but I don't have a nice example, but numerically we can show that such adapters can even create causal non-separability, meaning they can take a process that is Alice before Bob and they can give you back one that basically that is not even a convex mixture of causal orders, but is really causally non-separable. I don't have a nice example for that, but we really looked. Numerically, that is very easy to find, but I didn't find a good example to give you. So that seems a little bit powerful. So in a sense, it's a reasonable set of free transformations. It's the largest one. But you could say, well, that actually is maybe the reasonable set if Alice and Bob do not have access to this adapter. So if that change of their space-time, or sorry, of their process just comes from the outside and they have zero means of basically directly interacting with this adapter. Now you can go one step further and ask the question, well, what happens if Alice and Bob can actually use the adapter in order to possibly communicate? And what do I mean by that? Well, again, imagine this blue object, that's your adapter. And Alice can actually, instead of just plugging in a process, she's given this adapter and she can actually do something to it on her side. So she can plug some kind of operation like into it on her side, trying to communicate something to Bob. So she would basically take this adapter, plug something in on her Alice side, and then hope that by doing that, she can send a signal to Bob. So that's basically, she plugs this in, and then Bob gets a resulting object. If that depends on X, then Alice can actually use this adapter to signal to something. Now, in a sense, that should not be allowed because, again, we want a resource theory of signaling. So the adapters we use, the transformations of processes that we have, you should not be able to use them for signaling. So what we could demand is, or what we will demand, is that, well, no matter what Alice does up here, if she does an operation CX or an operation CY, what Bob sees on his side should not depend on that. Now, it should be completely independent of what Alice does. So that basically leads to the set of non-signaling adapters, that is, adapters that cannot be used to signal from one party to the other. Now, again, I depict this as this kind of ellipsoid, the set of all of these adapters. And they have very nice properties now. So first of all, they do not introduce causal non-separability, which is quite nice. And they cannot change the causal order of a process. So that means any process that is A before B will be mapped again to a process that is A before B, and any process that is B before A will be mapped to a process that is B before A. And that also means that I cannot out of blue make a process that is causally non-separable. So this is quite nice because it fixes two issues that we had with the adapters before. And certainly, and you can show this, but I don't want to go through the math, if I just demand this, we are guaranteed that we map processes to processes, and we are also guaranteed that we map free to free. And we really have this separation between the two because, as I said, we can't introduce causal non-separability, and we cannot change the causal order of processes, which are two things that these adapters in the brown set here and the admissible free preserving ones can do. So now we really get this, we start to get this kind of onion of possible free transformations. Now, this is certainly a reasonable set of transformations when Alice and Bob have access to the adapter, when they can use it to signal to each other. And we could go one step further where we say they don't only have access to it, but we also want them to implement those adapters. We also want them to implement the adapters themselves without using any kind of signaling. Or put differently, well, I've said these adapters can now not be used for signaling, but it is unclear if they can be made without any kind of signaling. So, the final thing that we could demand from our adapters would be that they can be implemented without any kind of signaling resources. What would that mean? Well, if Alice and Bob have their process, it would mean that basically the only adapters that satisfy this are those that can be implemented through shared entanglement between the two parties and local operations, like one in this slot, one set in this slot, one set in this slot. And these kind of like loose local operations and shared entanglement, these kind of operations have been kind of considered throughout the literature in this really nice paper by Gutowski and this really nice paper by David Schmidt. Yes. And again, we can look at the properties of these adapters. Certainly, they cannot be used to signal between the two parties because you can see that there's zero signaling resources that have been used. They cannot be used to signal between the two parties. By that, they can then also not introduce causal non-separability. They do not change the causal order. Basically, exactly the same properties as we had for the non-signaling set, but they actually form a proper subset of those, meaning that there are adapters that do not allow for signaling, but require signaling for their implementation. And a very nice example is the following one, which is basically just piggybacking, that's very nice, on this very nice paper from 2001, that kind of showed that there exist non-signaling maps between, say here, a non-signaling map would be one where Alice cannot signal to Bob down here, and Bob cannot signal to Alice. So there exist non-signaling maps that, however, require signaling for their implementation. Now, I can't go through that proof. It's a little bit of a lengthy proof, but just you have to take it at face value. So there are non-signaling maps that require signaling for the implementation. Now, out of these maps, I can actually quite nicely make a non-signaling adapter by just using two of them. So this is a nice non-signaling adapter. However, if it could be implemented with local operations and shared entanglement, then we could show that the first map you would have to be able to implement it in this way with shared entanglement and local operations. But this paper down here actually shows that there are non-signaling maps that do not have such an implementation. So kind of by contradiction, we get that, well, there are non-signaling adapters that really require signaling for their implementation, which is a little bit of a weird concept, to be honest, but it's quite nice that we get this separation of the adapters. So what we get is now really this picture of our free operations, of our free adapters, with which basically, depending on which one we choose, we get three distinct resource theory of causal connection. The free objects are kind of clear. That has to be the non-signaling processes. But here we can kind of pick and choose a little bit. But on the one hand, like the admissible and free preserving were too powerful, as we saw. The non-signaling ones are kind of easy to characterize. It's kind of nice. We can really work out what are the properties, but the implementation is a little bit unclear because some of them really require signaling in their implementation. And finally, the local operation shared entanglement set of free adapters is very nice physically, but it's hard to characterize. It's hard to characterize mathematically. So I think that is like the general crux in resource theories, that a lot of the times free operations, a set of free operations that is mathematically nice, is not the one that is physically the nicest. But because we wanted to do a little bit of computation, we kind of decided on just using the set of non-signaling adapters as the set of free ones. Okay, so this is kind of what we've seen already in terms of question of what can be transformed to what. We've seen already that with these kinds of adapters, we can not change the causal order, so we can't jump from here to here. We can't jump from here to here. We also can't, by that token, we also can't jump into the causally separable set, and we also can't create any causal non-separability, meaning that there is no causal order in terms of causal connection in the set of all processes, which makes a lot of sense. I mean, as expected, I would say. What we could ask, though, is, well, is there maybe a most resourceful process from which I can either get all the causal ones, or is there maybe a resourceful process, a most resourceful process from which I can get all the processes? Is there one from which I can start, and by means of free transformations, I can get all the other ones, which would then be really the prime resource? And it turns out that in the causally ordered set, we have this, at least for 2 and 3 parties. But in general, we don't. In general, there's no most resourceful process from which I can get all the other ones. Okay, so this is mostly it for the free transformations that we have. I'll get back to them in 5 slides. But I also promised you that we talk about quantifying signaling in processes. How do we do that? Well, as I said, one idea is basically to just take the distance of a process to the set of free states. So if you have a process here, you can ask, what is the distance to the set of the free processes? And the shortest distance that you have, that is basically how valuable your process is. And this can easily be measured by means of the signaling robustness, which is basically just the robustness of this W under mixing with other processes, or under worst case mixing with other processes, until I land up in this free set. And that's quite nice because it's a monotone of causal connection, meaning that whenever I apply a free operation to my W, afterwards the robustness of signaling is certainly smaller. That just comes from the fact that the free operations preserve the set of free states, free processes. So that's kind of a nice quantifier now of how much signaling is in a process. It doesn't distinguish between quantum and classical signaling. It just says how much signaling is in a process. Mathematically, it's kind of nice because I can phrase it in terms of an STP, which is not all that important, which has a primal and a dual problem. And the dual problem, as is quite often the case, is a very nice interpretation of this robustness. Namely, it basically, if you read this dual, it basically says, well, the robustness, the signaling robustness corresponds to the maximum like the maximum number of causal loops that I can close if I plug in an operation into my, say, A before B, that signals in the other direction. So basically it says, if you take your process, say, A before B, and you plug in something that allows you to signal from B to A, what's the worst you can do? How much can you break physics if you plug in basically this like if you basically close causal loops in this? So it's kind of a nice interpretation of the signaling robustness in terms of, well, if I had the power to, if Alice signals to Bob, to signal back to Alice, how bad would things get? How much would I break physics? That's kind of a nice intuitive interpretation of the signaling robustness. You could go through the math and compute it for different processes. You could compute it obviously for the non-signaling ones, it would be 0. For a process where basically Alice gets a state and then gets an identity channel to Bob, it's actually d squared minus 1, where d is the dimension of the system, which is actually the maximum achievable one. And you can also do it for like these causally disordered processes or for the causally non-separable ones, like the one introduced a long time ago by Reshkov, Costa, and Bruckner. And you find out that, well, they have like lower signaling than if you took your best case where like the signaling from Alice to Bob is perfect. I said earlier that there is a process in the set of causally ordered processes from which I can actually reach all the other ones. I want to show this quickly for two parties. So for two parties, this process is basically just the one with the highest causal robustness. Sorry, not causal robustness, robustness of signaling, which is basically just the process where Alice can perfectly signal to Bob. And in this case, you can very easily construct all other Alice to Bob processes by just plugging in a very boring adapter. So you plug in an adapter like that, and what you get in the end is basically the most general. If you think back to when I introduced processes from Alice to Bob, you get the most general process from Alice to Bob. So you can show that if you have this nice process that is just perfect signaling between Alice and Bob, and you use a free adapter, you can get all other processes that are signaling from Alice to Bob. That also works for three parties. It's just a little bit lengthier. Potentially not for four. I honestly don't know. For four parties, the robustness of this process that basically just has identities between Alice to Bob, and then an identity from Bob to Alice, and then from Bob to Charlie, and then an identity from Charlie to Dave, still has the highest signaling robustness, but potentially you can't reach everything from there. But I don't know. So as I said, and I'm coming to the end of the talk in like, give me 5 more minutes and I'll come to the end of the talk. As I said, in this set of processes, there's at least one on in the set of causally ordered ones from which I can reach everything in this Brown set. So there is like in the set of causally ordered things, there is a most valuable process, not just by monotone, but by actually we can always construct a transformation to get this whole set from up there. Same obviously from Bob to Alice. And now you can still ask the question, is there maybe in the, like up here, is there maybe a process from which I can reach everything else? Is there a process up here from which I can reach this process and this process by means of free transformation? And while I can't show that, like we haven't been able to prove that it doesn't exist, it is very unlikely to exist, because in a sense, what this process would have to contain at the same time is a process that perfectly signals from A to B and a process that perfectly signals from B to A. So it kind of would have to encapsulate perfect two-way signaling, which should not be a legal process. So that's my hand wavy argument for why this thing should not exist. And finally, I've drawn all of these arrows of all the transformations that are not possible. We also wondered, what about this set up here, the set of like causally non-separable processes, this lavender set up here? Is there maybe a total order in there, at least in that set? And it turns out that there isn't. Namely, there can be processes in that set, like say process 1 and process 2, where I can't transform process 1 to process 2, and I can't transform process 2 to process 1. And the way to show this is actually quite neat. You can construct them by first showing that the signaling robustness of process 1 is larger than the signaling process of process 2, which means that certainly process 2 cannot be transformed to process 1. But then you can also come up with a second resource monotone, which would in this case be the robustness of causal non-separability, which is the same idea of robustness, just not with respect to the non-signaling processes, but with respect to the set of causally non-separable processes, which is also a monotone in the resource theory of signaling. And you can see that the inequality is exactly the other way around, meaning that I also can't process, like if that holds, then I also can't map process 1 to process 2. So basically you can show that even in the set of causally inseparable processes, there's also no total order. Now that kind of leads me to my last slide, and we unfortunately will have to skip the technical interlude. We could obviously, like now I've done all of this for signaling. I mean, there's no reason why not to do it for causal non-separability. And I'd be very happy if anybody here is inspired to actually do this. This has been on my back burner for quite a while. So that would be kind of nice. So we could basically kind of play the same game, but now we don't say, well, our resource in a process is not the signaling, but it is the causal non-separability. And so again, we could play the same game. We could say, well, what we want again from transformations, they should be admissible. They should be free-preserving. And in this case, free-preserving would not mean to preserve the non-signaling processes. It would mean to preserve the causally separable ones. The third demand you could have is that it can't be used to create any causal non-separability. Before we said it can't be used to signal between the parties. And the last one is the demand that it can't be implemented. It can be implemented not with only non-signaling resources, but this time then only with only causally ordered resources. Yeah, so we played the same. We could play the same game, but now our free set is the dotted line here instead of before we had this set down here. And it turns out, well, yeah, you can play this game. The free preserving ones are kind of meaningful, but very hard to characterize. That's kind of an annoying thing. And kind of, yeah, they're tricky to actually pin down properly. The point that they cannot be used to create any causal non-separability actually doesn't add any additional restrictions on my set. So if I map sep to sep, if I map the separable processes to the separable processes, then the additional constraint of saying I can't create causal non-separability does actually bring nothing new. And finally, the demand that it can be implemented with only causally ordered resources, that actually leads to exactly the same set that we've already considered. So that would be kind of a boring, like that would be kind of the same resource theory that we had before in a sense. So the only, like, I think for causal non-separability, and I'm happily corrected, but I think there's only one meaningful resource theory about that, which is this one, which is a little bit hard to characterize as far as I remember. Okay, so now I had planned to do a little bit of a mathematical interlude for 10 minutes, but I think I'll skip this because I'm already over time. And I come to my conclusions and the open questions. So I hope that I've convinced you that, like, in the set of all processes, if we think about signaling, if you consider signaling a resource in processes, then there's kind of a natural set of free processes, which is exactly the non-signaling ones. And then we've kind of worked out 3 distinct sets of free transformations based on different levels of control, either adapters that are just given to you and you can't really interact with them freely, or you can use them to signal to each other, or you have to implement them themselves. So those were the 3 levels of control that we looked at. And in the paper, so I haven't done this in the talk now, but in the paper, we actually provide a full characterization of all the involved objects. And in order to quantify the signaling content of processes, we actually worked at a resource monotone, which has kind of a nice, clear operational interpretation. And we saw that there's no real total order in the set of processes. It's all kind of, it's a little bit of a mess, but we kind of get this nice shell of free transformations and these shells of processes, but like there's no total order in that set, as is to be expected, I would say. Some open questions that we still have. Well, quite often one is like, okay, it's nice to have an operational interpretation of the signaling robustness, but it would be nice to have kind of an information theoretic task that this relates to. So saying, if my signaling robustness is large, if of a process is larger than of another one, what task can I actually satisfy with a higher success probability? So far, we've only come up with like simulation tasks, which are a little bit not quite what we want. It would be nice to have like really a game to play where this pops up naturally. Another question is the question of, well, if I have this non-signaling set and the local operations shared entanglement, those two sets of operators. Well, so far we've only looked at like the purple set here, and we've looked at like what processes can be transformed into each other. But it might be that those two sets actually engender different hierarchies in the sense, well, like a question that I'd be quite interested in is, are there processes that can be transformed into each other via non-signaling adapters, but there's no local operational shared entanglement adapter that can transform them to each other? Something that I haven't touched upon is like general bounds for the signal robustness. So we can work out the largest, the bounds for that for particular cases, and for causally ordered processes, we can do it for arbitrary many parties. In general, we can only do it for 2 parties. And then 3 parties, we don't know what these bounds are anymore. So that would be quite nice to work out, like for general numbers of parties, how is the signal robustness bounded? As I said, it would be nice to work out a fully fledged resource theory of causal non-separability instead of causal connection. That was the actual original goal of this paper before we pivoted to causal connection. And finally, the same games can be played for a lot of other higher order resource theories. So for example, athermality. You could ask the question, well, what are the sets of higher order maps that map Gibbs preserving channels to Gibbs preserving channels, and then work out very similar questions. So I think there's a whole zoo of higher order resource theories that could be kind of derived in a very similar way. I want to finish with a shameless self-plug. I hope you kind of got interested a little bit, or those of you who haven't worked with higher order maps yet. Recently, together with a couple of colleagues, we wrote a long review and tutorial that hopefully is very pedagogical. So if you're interested, please have a look. Please have a look at that, and obviously also at the 2 papers that this work was based on. One where we actually work out the resource theory together with Jessica Barbaresco and Julie Kiribella, and one that has kind of, I would say, all the mathematical background that is actually needed, but was published 2 years later for several reasons. So those 2 papers is what this is based on. And with this, I apologize for being slightly over the time limit, and I want to thank you all for your attention, and I'm happy for any questions you might have.
Yeah, Simon, I have a couple of quick questions.
Oh, perfect. Yes.
For this local operation shared entanglement, is it same as local operation shared randomness?
I think local operation and shared randomness is, if I'm not mistaken, so I think there you really just share classical randomness, as far as I understand. So I think basically, again, I might be misrepresenting that. So if anybody knows this better, please do stop me before I say something stupid. But yeah, but I think for shared randomness, you don't share entanglement in the state. Basically, I think, if I'm not mistaken, you share like a separable state between the Alice side and the Bob side. That would be my understanding. I might be slightly wrong there. So please look this up. But just intuitively, this is my understanding. Yeah.
But I was just wondering whether they're the same things or. So another quick thing. So for the resource theory of causal non-separability, you have these sets, right?
Yeah.
In that, what is the place for non-Markov processes, which can, you had written a paper in 2018 that non-Markov processes will simulate this causal non-separability.
Yes.
Causally non-separable processes. So is there a relation there to non-Markov processes here?
Yes, I mean, okay, so you can still see my screen, I guess. So sure. the Markovian processes, I mean, so here this is a little bit, how do I put this? This is not ideal to connect this, because in order to use, let me go one step back. Let me go one step back, so that's maybe easier. Blah blah. Yeah. So if you have a process here, if it's Alice before Bob, it always ends on throwing away Bob's outcome. So in order to use this thing to simulate a causally disordered process, you kind of need an additional outcome line on which you can make a measurement. So what we showed in this paper back in the day was that basically you can condition, or you can post-select a condition, whatever you want to call it, by making a measurement on an extra leg that you put here. You can make a measurement, and then if you get the right outcome, say 0, then what you have implemented is actually a process that is causally non-separable. But that would require like an extra leg up here. So in a sense, it would require more parties. So if I wanted to connect this to like simulation questions of process matrices, I would need at least 3 parties. Because with 2, I can't do it. With 2, I don't have enough. In a sense, I don't have enough power for simulation. So like the simulation needs this extra leg on which I can condition. Now, where do Markovian and non-Markovian processes fit in? Like I think it's a little bit of a tangent. It's a different there we go. It's a different setup because Markovian processes can signal. So the most signaling process, this one, is a Markovian process. You know, it doesn't have any additional memory. So the most signaling one is actually a Markovian process. So in a sense, those two, like those ways of looking at each other, like memory, I would say, is a type of signaling, but this is maybe too blunt to distinguish between signaling that goes through the environment, like through an extra auxiliary line, and signaling that goes directly through the system. So I would say the question of Markovianity versus non-Markovianity distinguishes different types of signaling. One, like Markovianity would say there's only signaling that is transported through the system, whereas non-Markovianity would say there is signaling that actually goes through an additional auxiliary line. But both of them are signaling. So that's a little bit the like, I think this is too blunt to distinguish between those things. This is really just signaling content, no matter where it comes from.
Got it. Got it. Thanks.
And yeah, Simon, I also have a couple of quick questions about actually transformation of processes. So just to think possibly, can I think of them as, for example, anything that changes the Hamiltonian of the global system? I mean, if the process is associated with some system environment.
That is a very good question, which has a layered answer. So here, let me go back to the right slide so that I can talk about this. So here I basically think of transformations of W, so linear maps that act on W, and funnily enough, coming back to exactly your question, in this paper, these transformations were considered together with a constraint. So basically what they wanted to work out in this paper is what's the set of transformations of process matrices that is reversible and continuous. So they want like a family of transformations. So can I, like, basically, if I have two process matrices, I want to continuously and reversibly connect them. And what kinds of operations are then actually possible? And they worked out that the only sets of adapters that do that are kind of boring adapters, because it's adapters that have zero connection, like that are just local here, that just have a unitary here, or maybe in a symmetry, I don't know anymore, but like basically just local. And then people rightfully pointed out that, well, we can obviously go. And that would also mean, that I can never change the causal order with operations like that. Yeah, because I mean, if I only do something locally in a slot, there's no way of changing the causal order. And then people rightfully, I would say, pointed out that, well, but when we simulate the quantum switch, say, we can do it kind of continuously, you know, like it's slowly moving in the like beam splitter. Okay, I'm not an experimentalist, but like I can basically slowly do it, but that would kind of correspond not to transformations like this. These are really transformations that already take the process matrix as a given and then transform it. What you're talking to is basically changing under the hood, basically changing the building blocks that make up the process matrix. Those are different kinds of transformations. So in that sense, the question of what do you have control over? Is this process matrix given to you as a black box object? Then what I talked about are the most general sets of transformations. But you could say, well, maybe I have some parameter that I can, a knob that I can twist, like changing the Hamiltonian. That's a different kind of control. So in that sense, when you ask, do the transformations that I consider correspond to change the Hamiltonian, I would say no. They actually correspond to more like you can think of it more of a circuit, like where you have a black box thing, this W, and you plug it into the circuit and it gives you a new thing. So there's a big yeah, that's the difference, I would say. Again, the level of control in changing this W. I think of it in terms of black box.
I see. Thanks.
I think is there a question?
Are there other questions?
No, that's yeah, no.
Simon?
Yeah.
Really nice talk.
Thanks.
Do you have any ideas for constructing a complete set of monotones?
That's so yes and no. Yes. So we have there are these constructions for resource theories to kind of work out the complete set. So maybe for everyone who doesn't know what like complete set of monotones would be, where I can, because at the moment I can only say with my one monotone, I can only say if a transformation is not possible. I can say if the monotone for one process is smaller than for the other process, I can show that, well, there cannot be a transformation from the one with a smaller monotone value to the one with a larger monotone value. The other way around, though, doesn't necessarily hold. Like just because something has a larger monotone value than like process A has the larger monotone value than process B, doesn't mean that there's a transformation. Finding all monotones would mean that, well, if I have all monotones and all the monotones of one process are bigger than all the monotones of another, then that's an if and only if that the transformation is actually possible. So in this paper, we kind of used some results by Gilagur and Carlo Maria Scandolo, where they work out in a very abstract way all like a complete set of monotones that satisfy exactly this. So we worked that out in this paper, but it's absolutely abstract. It's like it's an infinite number of monotones that don't have any nice properties. So in a sense, I would say yes, we've done that, but in kind of it's almost a cheat. So we have worked out all the monotones, but they're not nice in terms of robustness or something. It's really just it's an infinite set of monotones that we actually worked out, which doesn't really, and none of them is really nicely computable. So I have no idea how to. So I have some ideas, to be honest, not for this resource theory, but for a resource theory where Gibbs preserving maps would be free objects, and then transformations thereof would be the transformations I consider. So there, I think there is a hope to have something like a free energy, to finding something like a free energy, because that has been done for quantum states. But I don't see a good way of finding all monotones in an intuitive way. So, I mean, yes, I can write down all monotones, but I can neither compute them nor are they intuitive at the moment. So I don't see much scope for that here. I see a little bit of scope for other higher order resource theories, like the one where you say, okay, I actually care about athermality. So that I can kind of see. Here, I don't know. I don't know how to. Yeah. Short answer is I don't know. Long answer is we've done it, but it's not very intuitive.
Good answer. Thank you.
Okay. I don't know if there are further questions. If not, thank you very much once again, Simon, for the.
Yeah, thanks all of you. And thanks really for giving me the opportunity. I've only talked about this like twice or three times so far because I never get the opportunity to do it. This was really good fun. I hope it came across.
Great.
Good. Okay. Have a good